In the previous section, we looked at biasing arrangements number 1 and 2, and those addressed cutoff and the linear region. We'll be looking at biasing arrangement number 3 in this section. Okay, this number 3 addresses forward biasing the base emitter and forward biasing the collector base junction. Current is high in all 3 junctions, mostly in the, let me turn on the pointer here for a moment, okay? Mostly in the collector emitter as previously discussed. This condition is called saturation. As the name implies, saturation means that the transistor is conducting as hard as it can. Its behavior is much like a short circuit with maximum current flow. The opposite of this would be cutoff. With cutoff, both junctions are open and reverse biased, and so we have essentially zero current. In saturation, we have maximum current. This represents the highest current condition for a transistor. This is the very highest current condition, and representative voltages, often you might see 0 volts on the emitter. You would probably see 0.7 volts on the base, and on the collector 0.1 to 0.2 volts is common, and this would represent a forward biasing of both junctions, and you would see maximum current flow. Saturation and cutoff are the conditions that are used in digital circuitry and hence microprocessors, etc. So saturation and cutoff would simply, you'd have the high and the low, and with digital circuits, remember, we are representing 0 and 1, so we would have a high and a low, and saturation and cutoff would represent those two values. Okay, biasing concepts. Important concepts to understand about transistor biasing characteristics are, okay, the first one we mentioned, the beta of a transistor, and the beta is the relationship of the collector current to the base current, and it is shown as IC over IB. Recall that we mentioned that the beta of a transistor is somewhat unstable. It is also referred to as HFE. Usually additional biasing is required to cause these to be stable. In their basic form, the beta, we mentioned one transistor, the 2N3904, its beta rating is 100 to 300, and that has to do with the relationship of the base to the collector current, and it can be 100 to 300 times larger. And that's just the spectrum that it can vary through. Okay, saturation represents maximum current flow. Cutoff represents no current flow. We also address the alpha of a transistor, and this is the relationship of the collector current to the emitter current. And as a rule, we say that IC equals IE, because if you go in to measure it, you're going to find that the current through the emitter to the collector is almost the same. Now, in theory, the way that they operate is that you have current flow. Some of it goes through the base, most of it goes through the collector. Remember that the amount that goes through the base is limited because the base is lightly doped with just a few holes, and in order for current to flow from the emitter to the base, you must have recombination. Only a few electrons will recombine with those holes, so we'll have limited flow through the base. Okay, biasing requirements. For various applications, certain conditions must be met for the circuit to operate properly. And so here we have an overview. We see we have applications here, the region of the transistor operation, and then the biasing requirements for the base emitter and the collector base. So if we're doing digital circuits, the two regions that we're going to be using are saturation and cutoff. And for saturation, both junctions must be forward biased. For cutoff, both must be reversed. So this is simply the on, and this is the off. For amplifier circuits, we're going to be operating in the linear region, and this is where the base emitter junction must be forward biased, and then, though it seemed like a contradiction, the collector base junction needed to be reverse. And so if we were to look at the outputs of a transistor, we would see that when we had the saturation and cutoff, this would represent either a very low value or a very high value, and this would come into play for representing zeros and ones in digital circuitry. But for amplifier circuits, we would see our output would be in between those two regions. And in linear region, in order for linear amplifier to be operating correctly, it can never enter into either saturation or cutoff. It has to operate in between, because the input must be identical to the output as far as the wave shape is concerned. Okay, this concludes our discussion on biasing, and the three conditions that we looked at were saturation, cutoff, and linear operation.